So in all my statistics classes and other classes related to statistics, I asked my students about how much TV do they watch on average each day. So here's a copy of the question my students see in one of their first assignments, and I've been doing this for many, many, many years now. And this is recreational screen time. In the days of COVID, right, we watch more instructional videos than we might have before. And so these are the rules. And I get a variety of answers. Now, we have been using Stackkey to simulate other samples to get a sampling distribution, and from the sampling distribution, we can get a confidence interval. Central limit theorem gives us a bit of information about this. So for example, use the central limit theorem, we say that the population average is going to be approximately equal to the sample average, right? That's our point estimate. And then to calculate the margin of error, for that, to get the confidence interval, I need some magic z-score. We call that sometimes z-star, and I multiply that by the standard error. And we've been getting that standard error from Stackkey in the randomization. Now, central limit theorem says that the standard error for a large enough sample size is going to be approximately equal to the sample standard deviation divided by the square root of the sample size. And as far as applying the central limit theorem goes, I can apply the central limit theorem under a couple of conditions. One, if my sample size is greater than 30, sometimes we even go with 30, or that I have a population of values that are roughly normally distributed, normal-like. And I'm just going to believe I have one or both of those assumptions met. You just got to have one of them met to use the central limit theorem to use this formula. So let's look at some data, see what we get, compare it to a simulation. So in Firefox here, I have my Google Sheet, and in my Google Sheet, I have the data from this spring statistics students, and here's the raw data over here. And I threw in a histogram, and I can see someone answer 10. Do they really watch 10 hours per day, or did they confuse the question and per week? And so when I write to students later and say, hey, did you really mean to answer this question? I often get the response back, oh, that's not right. I don't watch 10 hours a day. So I think that 10 is a mistake in the data that was submitted. So in this copy of it, I don't want to edit the original data. I'm just going to delete that 10. And so this is a histogram of the current student spring 2022 in my statistics classes. Now, is it safe to use this data for all college students? The answer is no, not really, for several reasons. One, this is a very convenient sample. It's not necessarily a random sample, and it's probably not representative of all college students in the US. And then what's the other problem? It's self-reported, right? I didn't actually watch and measure how much TV each of them watch and then take like a weekly average. I just asked them to guess at it. And maybe they underreport because they don't want to tell me they watch too much TV each day when they really do. Clearly this person that watches 5 hours a day isn't worried about that, but that's okay. All right, so what do we do next? So next, what we need is some summary statistics from that. Now, I shared with you earlier a spreadsheet that has a whole bunch of different tabs for different situations we come across applying the central limit theorem. I'm going to choose the one that's called CI mean with data. And here I actually have hours of day for 501 students. So for sure, I've been collecting this data since 2016. And so I had 501 students in statistics since 2016. And here's all of their numbers there. And I asked the computer to say, what's the confidence interval? So for 500 students, blow this up a touch more, I have an average of about 3.18 hours per day of TV. We have a margin of error on that for the confidence interval of about 3.3 hours per day, and that gives us a confidence interval of about 2.84 hours to 3.51 hours. What does that confidence interval mean? That would be what I think the average hours per day college students watch TV in general. Now these college students, if you look at the histogram, it's going to have a different spread than that right there. This is our estimate for the population mean. All right, let's get rid of this data. on, and then let's put in the data from this quarter. So here's my scrubbed data that has that 10 hours out. And this spreadsheet is linked in the video if you want to get to it. And here's my modified version of that spreadsheet I shared with you earlier. Just going to paste that in. And again, the spreadsheet's designed, if you enter your data in column A, then the spreadsheet calculates what you need. So it says here I have 32 students. Average hours reported was about 2.175 hours per day of TV for this group. That's going to be my point estimate for the population of all college students. I get a margin of error of about 3.37 hours per day. And again, since this variable is hours per day, the mean is hours per day, the standard deviation is hours per day, the standard error is hours per day, the margin of error for hours per day, everything here is hours per day, except for the alpha and T stuff. So based on this, I would say, well, it looks like on average college students watch about 1.8 to 2.5 hours per day. So let's double check a couple of things about that. Central limit theorem said that the standard deviation, sorry, the standard error for the sampling distribution should be about standard deviation of the sample divided by the square root of n. And in the spreadsheet, I've already programmed that formula in. So if we take a look at the standard error here, it says to take the standard deviation, orange there, and divide by the square root of the sample size. So there's the standard error. When, correction in my notes there, when we do means, we don't use z-scores, we use t-scores. So that z right there should be a t-score, t-star. And a t is like a z, it's a slightly wider distribution than a z, a standard normal distribution. And it's a little wider because not only do we not know the population mean, but we also don't know the population standard deviation. So we have to take account for both of those pieces of information we don't know, and with a slightly wider distribution. All right, so I take the confidence level, I'm gonna go with the 95% confidence level. That leaves 5% for the tails to split. That means each tail gets 2.5%. Based on that 2.5% and the sample size, I can calculate the t-score for that. And so if we look at my t-score formula, you can see I take the opposite from the t inverse using the left tail percentage, the 0.025. And remember, we have this idea of a t-score called degrees of freedom, which is always one less than the sample size, which is what I calculate next there. Let's double check that on Stackkey. So if I jump over to Stackkey theoretical t-distribution, first thing it says, hey, what's your degrees of freedom? Well, it's always the sample size minus 1. My sample size was 32, so I enter 31 degrees of freedom. Okay. And then I do a two-tail, 95 in the middle, and it says my t-score should be about 2.040 to 3 decimal places. Compare that over here. There's my 2.040. The nice thing about the spreadsheet is if I need more decimal places, I can just ask for more decimal places. So if the question I'm working on requires more accuracy than 3 decimal places, then the computer will give me as many as I need. So then the margin of error here in the spreadsheet just says, hey, take that t-score times the standard error. That's your margin of error. All right, let's make a quick sketch of this. So putting this all together, I always recommend you sketch this out to make sure you get the values in the right spots. In the middle of our distribution is our sample mean, and that was about 2.18 if we go to 2 decimal places. Now this is hours, and that's not 18 minutes, that's 18 hundredths of an hour. So again, this is TV hours per day for all college students. We are going for a 95% confidence interval. Boom, boom. So we put 95% similar samples in the middle there. And according to our spreadsheet calculations, we get about 1.80 as the lower estimate and 2.55 as the upper estimate for hours per day. And that gives us a margin of error, right? So that's roughly the distance from the center to the edge of about 0.37. Not 37 minutes, that's 37 hundredths of an hour. So that's our margin of error. So we're 95% confident that the that college students on average watch between 1.8 hours per day and 2.55 hours per day. That's our prediction. Compare that to a Stackkey randomization. You can do a Stackkey randomization if you have the original data, not just the summary like the mean and the standard deviation and the count. So let's copy that back to Stackkey. Stackkey should give us something similar. It won't be exactly the same for a couple reasons. Stackkey does randomizations, and we don't have a large sample size. 32 is big enough, but it's not really big, right? So we edit our data, delete, paste. Do I have a header row here? I do not, so I uncheck that box. Okay, and it should tell me my mean was 32. My count is 32. My mean is 2.175. Standard deviation is 1.037. Make sure that matches what the spreadsheet says. Yep, good. I got the data in there correctly, and then we generate and generate. How many? 5, 6, 7,000, somewhere in there. Let's go 7,000. Two-tail. Stackkey goes for 95% right away. Just thinking about it. There we go. Boom. Stackkey says, based on this simulation, we get about 1.827 hours to 2.535 hours, which is pretty close to what the spreadsheet said. And if I reset this and run it again, I'm going to get slightly different numbers down here, but they'll be in the ballpark. Notice the standard error Stackkey calculated here, which is 1.818. And spreadsheet says standard error should have been about 1.83. Are they the same? No. Are they similar? Yes. So again, this is theoretical prediction. This is a randomization. Each randomization will be slightly different, but they'll all be in the ballpark of each other if your sample size is big enough, at least 30. All right, that's it for this one. Check back for a hypothesis test.